Hello everyone, I'm Libington. I will be presenting our learning-based approach for consistent video depth estimation. I will begin by describing our goal, which is to generate the consistent depth maps from a molecular video. Depth estimation from a video sequences plays an important role in many computer graphics and visual applications, such as view synthesis, video stabilization, scene understanding, among others. While there has been extensive research on single image depth estimation, these approaches produce geometrically and temporally inconsistent results on video sequences. As you can see, their generated depth maps suffer from severe flickering. Several methods specifically focus on handling videos, which I'm going to discuss by classifying them into two categories of constraint training and test and optimization. For constraint training, some approaches propose to estimate depth of a video by training a network using multi-view loss functions. However, these approaches are inherently designed for static scenes. Several approaches propose to implicitly enforce temporal coherency through recurrent neural networks. However, these approaches do not explicitly enforce the final depth maps to be geometrically consistent. Li et al. Proposed to fine-tune a single image depth estimation network using unlabeled video datasets by enforcing a set of geometrical and temporal constraints. While this approach produces reasonable results for videos that are similar to their fine-tuning datasets, it often struggles to generalize to unseen videos. To address these issues, test and optimization techniques fine-tune a single image depth estimation network on the test video to improve the geometrical and temporal coherency of the results. The core idea behind these techniques is that the corresponding points in any given two frames come from the same 3D points in the scene. Therefore, given these frames and their correspondences, they further use a single image depth network to generate the depth maps for these frames. The corresponding points are then projected into the 3D space using the estimated depth at these pixels. The distance between the projected 3D points is used as the objective for fine-tuning the network. By doing this fine-tuning, these methods force the network to produce depth maps that are geometrically consistent. However, they have two major problems. First, during optimization, they need to evaluate a complex loss that involves pixel reprojection, making their approaches computationally expensive. Second, these methods equally rely on the geometrical constraints during optimization. However, the geometrical constraints come from the correspondences that are computed using existing optic flow approaches and may be inaccurate, as shown here. Enforcing such inaccurate constraints leads to suboptimal results, as shown on the right. Note the missing fine in the estimated depth maps. Our key idea is to address these issues by pre-computing a set of pseudo-reference depth maps according to each frame, and optimize the single image depth estimation network by minimizing the distance between the estimated and pseudo-reference depth maps. By pre-computing the pseudo-reference depth maps, we eliminate the need for evaluating a complex loss during optimization, making our method 2.5 times faster than test time optimization approaches. Additionally, we construct the pseudo-reference depth maps by discarding the unreliable geometrical constraints, therefore producing better results, as shown here. Now, let's see how we calculate the pseudo-reference depth maps for each frame. Consider this pair of frames and the corresponding pixels in the two frames P and Q, obtained using optical flow. Our goal here is to calculate the optimal depth for pixel Q in image I, considering the corresponding pixel P in image J. The 3D points corresponding to pixel Q could be anywhere on this line. I'm showing 5 of such points here. These points project to the epipolar line in the other image. The optimal 3D point is the one that, when projected to image J, has the minimal distance to pixel P. Fortunately, this can be calculated in closed form. See the paper for details. Performing this computation for each pixel of image I gives us a pseudo-reference depth at image I considering image J. For each frame, we can perform this process considering a few frames to obtain a set of per pair depth maps. Next, we would like to aggregate these depth maps and obtain a single pseudo-reference depth for this frame. One option is to average these maps. However, this approach assumes that all the estimated depth maps are reliable. Unfortunately, because of optical flow inaccuracy, some of these depth maps contain inaccurate estimates. For example, looking at the input image, we can see that the person is standing behind the board, and thus should have a slightly larger depth than the board. However, if we look closely at one of these per pair depth maps, we can see the person's depth is smaller than the board. Therefore, averaging all the per pair depth maps results in inaccurate prediction in this region. To mitigate this issue, we obtain the per frame depth using the median operation. This operation considers the value that is agreed by the majority of the per pair depths and thus discard the outliers. As shown in this insights, median strategy produces better results. To summarize, we compute a per frame depth map for each frame and optimize the single image depth network by minimizing the distance between the estimated and the pseudo-reference depths. Since the pseudo-reference depth is computed according to the geometrical constraints, minimizing this loss encourages the system to produce geometrically consistent depth results. Additionally, we minimize the distance between the estimated depth maps of two consecutive frames after projection to 3D space to encourage the results to be temporally consistent. Our total loss is the combination of them, while lambda controls the weight of the consistency. We will show the effect of lambda later. Our approach backpropagates the total loss to fine-tune the network to achieve geometrically and temporally consistent results. Now, let's take a look at our results and comparisons against the state-of-the-art methods. we first show quantitative comparison against the other approaches on the TUM RGBD datasets. The error metrics are absolute relative error between the estimated and ground truth depth values, squared relative error, root mean squared error, and root mean squared error in the logarithmic domain. For all these metrics, lower values are better. MC is a single image depth estimation method, and we use it as our base network. These are video depth estimation methods that perform constraint training. These are test time optimization methods, similar to our approach. As shown in bird values, our method outperforms the other algorithms across all the metrics. Now, let's look at some visual comparisons. You can see that MC, which is a single image depth estimation method, produces results with significant flickering. Our approach uses MC as the base network and produces geometrically and temporally consistent results. CVD, which is a test time optimization method, similar to ours, also produces coherent results. However, their results are less accurate. Let's focus on a single image to see the differences. Because of enforcing all the geometrical constraints, even the inaccurate ones, CVD often produces overblurred and inaccurate depth maps in challenging regions, as shown by the arrows. Our depth maps are generally sharper and more detailed. I would like to also note that our method is 2.5 times faster than CVD. Now, let's look at another thing. Again, our method produces coherent and high-quality depth maps that are significantly better than MC, the single image depth estimation method. Focusing on a single frame, we can clearly see that the depth from CVD is over-smoothed and lacks detail in the regions indicated by arrows. Let's see another thing. Here you can see that CVD is not able to properly estimate the depth of the fast-moving fan. Our approach, on the other hand, produces results that are both detailed and coherent. Looking at the single frame, we can see that in addition to not being able to estimate the depth of the fan, CVD overblurs the hand boundaries, as shown here, and incorrectly predicts the depth in the gap between the arm and the body, as shown by this arrow. Let's see one more comparison. This is a scene with faster local motion. Our method produces geometrically and temporally consistent results. Taking a closer look at a single frame, we can see that CVD struggles to properly handle both the moving regions like the jaw and the static regions like the table leg. Now I'm going to discuss one ablation study. Specifically, here we are evaluating the effect of lambda, which provides a balance between temporal and geometrical consistency losses. Using a small lambda, we are not able to properly enforce the temporal coherency and produce results with flickering on the hand and other regions. Using a large lambda, the temporal consistency term overpowers the geometrical consistency loss, producing over-smooth results. Lambda equal to 0.3, which we use in our work, provides a good trade-off between temporal and geometrical consistency of the results. In conclusion, we presented a novel test-time optimization approach for estimating geometrically and temporally consistent depths from a molecular video. Specifically, we introduced pseudo-reference depth maps to significantly reduce the computational complexity of the optimization. Moreover, we propose a strategy to discard the erroneous pseudo-reference depth maps computed from pairs of images to obtain a per-frame pseudo-reference depth. We demonstrated the efficiency and effectiveness of our approach through comparisons against the state-of-the-art methods, both visually and numerically. Thank you.